Welcome to the Deep Dive. If you're someone who often needs to get up to speed, like really quickly on complex research topics, the kind that stretch across tons of papers and data, then you know how tough information overload can be. Today, we're diving into some fascinating research about a new AI framework. It's called WebWeaver, and it's specifically designed to tackle that exact challenge. We've been looking at the source material, and it zeroes in on something the researchers call open-ended deep research, or OEDR for short. This isn't just asking a quick question, it's more like conducting a full investigation.
Right. And what's really striking about OER is the sheer scale and complexity involved. We're talking about an AI needing to sift through, digest maybe over 100 different web pages, PDFs, a huge amount of information. And the goal isn't just a summary, it's to produce a detailed, verifiable report with genuinely synthesized insights. The amount of text it involves can easily top 100,000 tokens.
Wow, okay. That sounds like a massive hurdle for most AI systems we see today. So our mission here is to unpack how this WebWeaver system gets around the big limitations that stopped earlier AI attempts. It seems like they're swapping out rigid, machine-like processes for something more organic, more human.
That's a good way to put it. And to really appreciate what WebWeaver does, we should probably first talk about those limitations in the older systems. There were two main flaws, really. The first one comes down to static pipelines. See, a lot of older research agents planned everything first, then when looking for evidence. Think outline-guided search.
Ah, okay, so they'd create the whole structure up front.
Exactly. But that initial outline was based entirely on the large language models' existing knowledge, which is often out of date. So the plan gets kind of fossilized right at the beginning.
Which means if the AI finds something really important or surprising early on in its search, it can't easily change the plan, right? It's stuck with those initial assumptions.
It is. The research path is basically locked in, no matter what the actual evidence says later. It limits adaptation. Then there's the second big problem, one-shot generation. These systems would just gather all the material they found, maybe that whole 100,000 plus tokens, and try to feed it all into the AI at once to write the final report.
And why is that? Well, why doesn't that work well?
Well, it runs straight into major problems with processing really long inputs, what they call long context failures. You probably heard of loss in the middle.
Yeah, where the AI kind of forgets the stuff in the middle of a long text.
That's the one. It focuses too much on the beginning and the end. But beyond that, trying to make sense of so much, often loosely related, information all at once, just skyrockets the chances of the AI hallucinating, making things up. It really hurts the report's accuracy.
Okay, that paints a clear picture. It's like asking someone to read 100 different articles and then write a perfect summary immediately. They're bound to forget key details or miss connections. A human researcher, they wouldn't finalize their whole book outline before doing a lot of reading, right? And they definitely wouldn't read everything cover to cover before writing sentence one. The outline evolves.
Right. It's a living document for a human. And that kind of coevolution of planning and discovery, that's the core idea WebWeaver is trying to mimic. Which brings us neatly to WebWeaver's design. It's a dual-agent setup. There's a planner and a writer. The idea is to mirror how a human researcher might actually work. So the planner is all about that exploration and analysis part. Its big innovation is this dynamic research cycle. It keeps switching between finding evidence using search actions and refining the plan, the outline using write outline actions. It interleaves them.
Okay, wait. If the outline keeps changing, how does it avoid just wandering off? How does it know when it's got enough evidence or manage the scope so it doesn't get lost?
Good question. That's where the structure and, crucially, the grounding come in. The planner isn't just making a vague structure, it's building a detailed, source-grounded outline. What that means is every single part of the proposed outline is directly linked through explicit citations back to the actual evidence collected in a kind of memory bank. That grounding keeps it focused and verifiable.
So the planner's final output is like a really detailed blueprint, and every claim or section idea already has footnotes pointing to the proof.
That's it. When it's acquiring evidence, the planner uses the LLM for two things. One, distill a summary relevant to the query, which helps guide the next search and keeps the outline context updated. And two, extract specific verifiable details, quotes, data points, that kind of thing, which go into that structured memory. And we know this back and forth is important. The data shows the planner typically gathers something like over 67,000 tokens of evidence. And the outline itself, it gets revised more than twice on average, ending up as these quite complex 4,000 token outlines. It shows you really need that dynamic approach.
Okay, so the planner builds this detailed evidence-backed structure. Then the writer steps in. How does the writer avoid that long context problem, the one that tripped up the older systems?
The writer uses a very different approach.
Yeah.
Section-wise, hierarchical synthesis. It tackles the report piece by piece, following the planner's outline. For each section it needs to write, it does a targeted retrieval. It only pulls the specific pieces of evidence from the memory bank that the outline citations say are relevant for that specific section. So instead of wrestling with 100,000 tokens, it might only need to look at, say, a few hundred highly relevant ones for a single paragraph. And before it writes, it uses an internal step called a think action to sort of process and synthesize that retrieved information.
Tell me more about that think action. It sounds like pausing to reflect. What's happening there?
Yeah, it's basically forcing the AI to go beyond just stitching quotes together. It's like a human researcher looking at maybe 5 key pieces of evidence and figuring out, okay, what's the real connection here? What's the logical flow? Then it starts the right action. It enforces a kind of information discipline. And once a section is done, the source material used for it is effectively cleared from the immediate context, pruned. This stops the context from getting overloaded and prevents unrelated information from bleeding into the next section. It builds the report block by logical block.
Right, makes sense.
Right.
So the big question, does this whole sophisticated human-like approach actually deliver? Did it perform better? The research indicates yes. WebWeaver apparently achieved state-of-the-art results on some pretty tough OEDR benchmarks like DeepResearch Bench, DeepConsult, and DeepResearchGym.
We can definitely tie that performance back to the design choices. Let's take source groundedness. On DeepResearch Bench, WebWeaver hit a citation accuracy of 93.37%. What that really means for you, the user, is trust. You can be confident that almost every fact or claim in the final report is correctly linked back to its original source. That's huge for tackling the verifiability problem in AI-generated reports.
That's incredibly important, yeah. High accuracy, and you can check the sources. What about the dynamic planning part? Did that prove its worth?
It did. That relates to dynamic planning efficacy. They actually tracked how performance changed based on how many times the planner refined the outline. The results were clear. The more optimization cycles, the better the final report scores. This showed up particularly in structural metrics on DeepResearchGym, things like depth and breadth of coverage. They got really high scores, near perfect in some cases. It basically confirms that letting the plan evolve based on what's discovered is essential for comprehensive, well-structured reports. And finally, the writing method itself. They did a comparison, an ablation study, pitting the section-by-section hierarchical writing against the old brute force method, feeding everything in at once. Hierarchical writing won out significantly across the board. But the most striking difference was in a metric called insight. It jumped from about 41 up to over 50.
So that jump from 41 to 50 on insight, that's basically the difference between getting a flat summary versus a genuinely insightful analysis that actually adds value.
That's a great way to think about it. It shows that focusing the AI's attention on just the relevant evidence for each specific point is crucial for generating reports that are not just accurate, but also coherent and, well, insightful. You get synthesis, not just summarization.
The research also mentioned something about agentic fine-tuning, using a WebWeaver 3K dataset to teach smaller models. Can you elaborate on that? Why was that needed if it worked with big models?
Right. The goal there was really about making this capability more accessible. Could they get smaller, more practical language models to perform these complex OEDR tasks, not just the giant, expensive ones? So they created this data set of successful WebWeaver runs, thinking, searching, writing steps, and used it to fine-tune a smaller model, like Quinn 330B. And the result was pretty dramatic. Before fine-tuning, the smaller model's citation accuracy was terrible. Around 25%, you couldn't trust most of what it said. After fine-tuning on these examples, it jumped to almost 86%.
Wow, from 25% to nearly 86%.
Yeah. It's strong proof that this complex research process can be broken down into learnable steps, demonstrations of thinking, searching, writing. It means these powerful research skills aren't necessarily limited to just the biggest models anymore. Smaller, more deployable models can learn to do it reliably too.
Okay, so if we were to boil down the core takeaway from this deep dive, it seems WebWeaver's success comes from effectively translating how humans actually do complex research, that dynamic planning, constantly checking evidence, writing in focused chunks into a set of concrete actions an AI can follow.
I think that's right. And this research really reframes the challenge of dealing with long documents or massive amounts of information. It suggests that getting high-quality, comprehensive reports isn't just about having a bigger memory or context window to stuff everything into. Instead, it's about smart, system-level information management. It's about orchestrating the workflow through deliberate actions, like targeted retrieval and structured planning. Quality seems to come from the process, not just the raw capacity.